Have you ever heard the phrase, black holes have rings, and assumed it's just the glowing accretion disk making a neat halo? Here's the twist. Even if you turn off the disk, no matter falling, no hot gas, there can still be a ring-like pattern in the light we receive. Not because photons are orbiting forever, but because near a black hole, photons can execute an unstable choreography so sensitive that a tiny change in their path changes where they end up. The result is a bright photon ring, a thin feature that encodes the geometry of the spacetime itself. But the deepest reason it forms isn't just gravity, it's chaos. More precisely, Lyapunov chaos, where divergence between neighboring trajectories grows exponentially. The question is, how can something unstable leave a stable fingerprint? And what does that say about how we infer an invisible object, using light that can't quite decide where to go? To understand the before, imagine astronomers looking at black holes through a fogged lens of ignorance. Before detailed simulations and before the Event Horizon Telescope era, the prevailing expectation was that black hole images would mostly reflect messy astrophysics, turbulence, magnetic fields scattering in plasma, and the uncertain structure of the accretion flow, the shadow of a black hole. Its dark silhouette against bright background light was predicted, but translating that prediction into sharp observables was hard. Even when models produced a crescent shape, the clean connection between observed brightness and the underlying spacetime metric remained indirect. Theoretical work had long described special null geodesics, photon spheres where light can circle. Yet, photon sphere sounded like a perfect ring, like a stable track you could ride. In reality, that orbit is unstable. A photon can be temporarily trapped, but it will eventually peel away, either plunging into the black hole or escaping to infinity. So the before state was the black hole's shadow exists in principle, but the detailed ring structure, especially its chaotic origin, was not yet made tangible in how we interpret images. Now, the core mechanism, picture a black hole as a drain in a whirlpool. The geometry of spacetime acts like a moving, warped map. Photons follow geodesics, the shortest paths in that curved map. There exists a radius where, in just the right conditions, a photon's angular motion and gravitational pull balance, forming the photon sphere. But the balance is like balancing a pencil on its tip. Any slight wobble grows. Mathematically, the instability can be captured by Lyapunov exponents, which quantify how fast two initially neighboring trajectories separate. In the simplest terms, if one photon's impact parameter differs infinitesimally from another's, their later positions diverge exponentially as they loop near the black hole. That exponential sensitivity is the signature of chaos. Here's how the ring emerges from this instability. Consider photons coming from a bright background. Some are captured on the first pass, some escape, and a narrow subset perform multiple near orbits. Each additional loop corresponds to a photon spending more time skimming the photon sphere region, which changes the apparent position of where it arrives. Because the instability grows rapidly, only photons with impact parameters tuned to a precise set will complete, say, one loop rather than being deflected out sooner. Those finely tuned trajectory cluster in where they appear to a distant observer. The photon ring is essentially a locus of apparent directions where photons with different loop counts converge in the image. The ring is thick in practice because the tuning is never infinitely perfect. Plasma effects, finite resolution, and emission physics blur the idealized picture, but the underlying structure is geometric. The spacetime funnels certain sets of light paths into a recurring bright feature. This is why a supposedly unstable motion produces a robust observable. The system isn't stable in time for a single photon, it's stable in pattern for a population. But geometry acts like a filter. Despite chaos, it preferentially maps many initial conditions into similar final directions after one or more near orbits. Numerical relativity and ray tracing through general relativistic spacetimes make this explicit. As you zoom into the image, you see layers corresponding to photons that loop different numbers of times before escaping. The broader implications are bigger than one ring. Lyapunov chaos connects black holes to a general theme. Many chaotic systems have a characteristic rate at which information about initial conditions is lost. In gravitational physics, those rates relate to deep principles about entropy and horizons. If the photon ring structure encodes the spacetime metric through chaotic light dynamics, then high-resolution imaging becomes a kind of spectroscopy of geometry. It's not just, does the shadow look right? It's, does the chaotic lensing behave like the predicted unstable geodesics of a specific black hole model? That matters because future instruments can measure finer features, ring thickness, brightness profiles, and deviations that might hint at spin, charge, or departures from the simplest Kerr picture. Moreover, photon rings provide a pathway to test general relativity in the strong field regime using real photons in real astrophysical environments. Chaos is usually considered a complication, but here it becomes a diagnostic tool. The exponential divergence means small modeling errors or uncertainties could in principle magnify, yet the ring's existence shows that geometry leaves an imprint resilient enough to survive. That resilience suggests we can infer an object we cannot see by exploiting the deterministic chaos of light near the horizon, turning unpredictability into a measurable signature. So what did we learn by following the light's unstable paths? We started with a misconception. A ring around a black hole isn't guaranteed to come from glowing matter. Instead, gravity can create a photon ring, light that repeatedly skims an unstable photon sphere. The orbit is not stable. It's governed by Lyapunov chaos, meaning nearby trajectories separate exponentially. Yet that instability yields a stable fingerprint because many photon paths, once processed by the same spacetime geometry, converge into similar apparent directions. The ring is the map of chaotic geodesics, and it hints at something profound. Horizons don't just swallow light, they organize chaos into structure we can observe. If you want more on how the universe turns instability into penetration, subscribe for the next breakdown.